Hello students, so let us continue with our journey on cryptography. So here we have a diagram where we see some XOR operations going on. So these are representing the XOR operations, and input is nothing but say plain text and a key. This plain text and this key will have same length, and when the XOR operation is done, the output is also going to be of the same length. So all these components that we are learning is in order to understand how DES algorithm works. DES is data encryption standard. So we are going to see step by step how these are combined in order to execute the DES algorithm. Here we have a rotation cipher. So what happens here is we have an input. Suppose we have 5 symbols or 5 letters or 5 numbers. Now they are going to be rotated. So the second one will go to the first, the third one go to the second, then the fourth one will go to the third. Okay, it will happen in a rotation manner, and if we follow this convention, then the first one will go to the last. So we just need to rotate the bits that we have. Okay, it's like bit shifting that we do. So this is rotation cipher, this is XOR cipher, and then we have S box. So S box is nothing but substitution box. Here we will have suppose n input bits, so function that maps n inputs to m outputs. So suppose we have an input of a certain length, but we want the output to be of a different length, then we can go for substitution boxes. So it's like a matrix formation where certain collection of numbers can be represented by a new number or symbol. Okay, so here you can see the length is big, but here the length is small, so the output generally is a smaller one compared to the input. Okay, we have this substitution box. Then we have something called permutation box. So it is P box. Earlier it was S box, now it is a P box. So what happens here is, suppose 1 goes to 4, then 2 goes to 1, then 3 goes to 5, then 4 goes to 3, and 5 goes to 2. So that is fine. That is a simple straightforward jumbling that we are doing. I suppose we have done a similar way of substituting various symbols with other symbols. Okay, but here we can do something more. We can also go for expansion, or we can also go for compression. So in expansion, what happens is, suppose we have 3 symbols, 1, 2 and 3. Suppose the output length needs to be 5, so we are going to do some redundant placement of the symbols. So 1 will not only go to the first place, but it will also go to the 4th place. 2 will suppose according to this diagram go to the 3rd place, and the 3rd one will go to the 2nd place and 5th place. Okay, so here we are trying to extend the particular value or particular input that we have to a larger one. And we can also do the reverse, which is known as compression. So here we can see we have 1, 2, 3, 4, 5. Here we are taking only certain inputs in the output. Okay, so as some symbols are going to get discarded, we are going to be left with a smaller number of symbols in the output. Okay, we have to go for this kind of strategy in order to make things complex enough for others to crack it. Okay, it cannot be a random way of shifting the various inputs to outputs. Of course, if we stick to a particular plan, then we have to continue with that plan. Okay, because see, if the sender sends the information, the receiver should be able to do the reverse of it, right? So in order to do that, the information shared by the sender and the receiver has to be same. Fine. So then we come to this DES. Okay, so this is a kind of a diagram that represents DES, data encryption standard. So normally what happens in DES is we are going to have a 64-bit plain text. So a plain text can be of any length. However, we are going to take 64 bits at a time, and we are going to put it as an input. Okay, so initially there is going to be an initial permutation. So I think we have already gone through the concept of permutation here, right? So we are going to go through an initial permutation, and then a certain number of rounds are going to take place where certain operations are going to run. Okay, so in standard DES, what happens is we are going to have 16 rounds where a particular key is going to be fed to that particular round. So from where will that key come? Well, that this individual keys that you see in each of the round comes from a particular key which must have the same length as the plaintext. So plaintext has 64 bits and the key also has 64 bits. Okay, so now there will be a round key generation. So in each of the rounds a new key will be generated which will be derived from this 64-bit key. So that's why we don't have the same keys here. We have different keys and they are named or labeled differently. We have K1, K2 up to K16. Okay, and then once these rounds occur and they finish, the final output is again going to go through a final permutation, and then 64-bit ciphertext will be created. So from plaintext we have obtained a ciphertext, and then this ciphertext can go through the network to the receiving end. Okay, so let us move forward. Now one round in DES cipher, here we are trying to see what really happens in a particular round. Okay, earlier diagram we saw that we have 16 rounds occurring in a particular DES algorithm from the input to the output, but what really happens inside? And in fact, in case of the receiving end, the reverse is going to happen, right? In the earlier diagram we see only the encryption part, okay, or we only see what happens in the sender part. In the receiver end, the reverse is going to happen. So whatever strategy we apply here, the reverse is going to take place in order to again obtain the plaintext. So what happens here is initially we had 64-bit plaintext, isn't it? So it was in the previous diagram. So from 64-bit we are going to make two parts. We are going to make 32 bits and 32 bits. So we are going to label them as left and right. And in one single round, because this slide concentrates on a single round, so in one single round what happens is, see, this R is going to have 32 bits, and the key that is fed inside this particular round will be of 48 bits. However, in this diagram we see 64 bits, so that means there must be some computation going on such that this 64-bit key becomes a 48-bit key. So once this 48-bit key is generated, it is going to go through a particular function. So in this function, what are the inputs we have? We have the right part of the plaintext and the key itself, and then we are going to obtain an output which will be of the same length as R. Okay, R was 32 bits, so we again have 32 bits here. Alright, so let us keep R at this place and let us look at the left side. So from left side we are going to put it in a particular XOR operation, and this input is of 32 bits, right? So this input is of 32 bits and we already have an input of 32 bits from the right hand side. So this 32 bits and 32 bits, they are going to go through an XOR operation, and then we are going to obtain the output which will also be of 32 bits. Okay, so the first place of this information will XOR with the first place of this information, second place of this information will XOR with second place of this information, okay, and similarly all the 32 bits will be generated and it is stored here, and then we directly take the right part of the plaintext and directly put it in the left side. Okay, so we are preparing for the next round. Okay, this entire computation that you see in this particular slide is created, or it is run in order to obtain the input for the next round. Okay, so now we look at the right hand side. We have the decryption rounds shown here. So what happens here is we have the left part that goes to the right hand part. Okay, and then this information is again going to go through 32 bits, and the corresponding key of the round is going to be fed inside this function. So this function is going to have this 32 bit and this key of 48 bits, and then a 32 bit output will be created, and these will go through XOR. So what will go through XOR? This 32 bit information that has been created and the right hand part that we already have, because now we are going to go from down to up, because this is the description this is the decryption round, right? So we are going to do the reverse. So here again we are going to go through XOR to obtain the left side for the next round, okay, or for the upper round. All right, so please go through this little bit more. Okay, try to know the significance of XOR, try to understand why the lengths of this information or inputs need to be same. Okay, so let us move forward. So this is a des function. So what happens here is we are going to go through a function, right? Here it seems like a black box. We have simply said that we are going to have a function which will have 32 bits as an input from the data and 48 bits from the key. So what really happens here is once the 32 bit comes as an input, we are going to go for a expansion permutation. So when we put inside the function, it is going to take the data part and then it is going to go for expansion, and then 48 bit is going to get generated. Okay, so from the data we have 48 bit generated, and from key we already have a 48 bit waiting for us. So now we have both the inputs of same length. So we have 48 bits from the data and 48 bits from the key. So they are going to go through an XOR operation, and then we are going to obtain a 48 bit output. So this 48 bit output is again going to go through a substitution box. That is, some of the bits will be omitted, okay, and some of them may be replaced or jumbled, okay, and then the new output that we obtain is going to be of 32 bits, and it is going to go through a straight permutation. You have already seen the diagram of straight permutation before. So from this 32 bit input, we are going to obtain a 32 bit output. Okay, so this is what really happens in this particular box. Fine. Then we can also go for triple DES. So here again we have a 64-bit plain text, and it is going to go through more DES encryption procedures than one. Okay, in the previous case, all the rounds we had and all the functions or all the concepts that we learned was for a single box. Okay, if you consider yellow box to be one DES algorithm, then we had one single box. But here we have multiple, and in that case we are also going to require multiple keys. Okay, and here we are talking about this particular key here. Okay, we are talking about this particular key. So in case of triple DES, as the name suggests, we have to go for DES 3 times. So we are going to require 3 different keys for each of the DES procedures. Okay, so 1, 2 and 3. In the decryption end, we are going to do the reverse. Okay, and the keys will also be used in the reverse way. So we are going to first use K3, then key 3, then key 2, and then key 1.